A warm welcome back to all NSCAS geography learners and others who are interested in learning more about the natural wonders of geography. This is lesson 2 in a series of 5 radio learning programs. If you joined us for lesson 1, you will remember that we discussed the Earth's or the global energy budget. And now in lesson 2, we will learn about the local energy budget. If you are a NEMCOL student, you will find this topic in your NEMCOL NSCAS geography textbook in the chapter on physical geography, atmospheric processes. At the end of this lesson, you should be able to distinguish between sensible and latent heat transfer, draw the daytime and nighttime model, define albedo, and describe how it varies with different surface covers, and describe and explain the local energy budget. It sounds like a mouthful for me and an earful for you. So let's get started. You probably want to know what this local energy budget is. The local energy budget refers to the amounts of energy that reaches the Earth's surface, warms up there and leaves again, referring to one specific location over a 24-hour period. It is important to understand the definition in terms of all these elements, because in an exam, you should be able to explain local energy budgets in terms of input and output analysis, with reference to the daytime and nighttime energy model. Don't worry, it will get clearer. Let's start by talking about the daytime local energy budget. The daytime energy budget refers to the balance of energy during the day, and it has 6 components. These 6 components are incoming solar radiation, reflected solar radiation, surface absorption, sensible heat transfer, latent heat transfer, and long-wave radiation. In ordinary language, we are simply talking about where heat is generated in a certain area. Well, we'll talk some more about each of these components. Just remember, you should not only recite the definition of the local energy budget, but should also explain how the energy budget is achieved. This is referred to as the gain, transfer, and loss of energy during a daylight period. So let's look at the 6 main components of the daytime local energy budget. Incoming solar radiation or insolation. Can you remember from lesson 1 that sol means sun? Incoming solar radiation or insolation is simply the incoming sunshine, which is the main energy input. The amount of sun energy a place gets depends on the latitude, meaning how high or low its location is. It also depends on the season. Summer is hotter than winter. And it depends on cloud cover, because clouds shield a place so that the sun rays cannot get through effectively. Thus, less cloud cover and or higher clouds means that more sun radiation reaches the Earth's surface. Secondly, reflected solar radiation. This is sunshine reflected back from objects on its way to the Earth's surface. Reflected solar radiation is called albedo, as you know it, and it is varies in color because light and shiny materials reflects more sunshine than dark materials. Interestingly, blades of grass, which are mostly yellow in Namibia, have an average albedo or reflectivity of 20 to 30%. Can you imagine? Up to a third of the sun rays falling on grass are reflected back. The third component of the daytime local energy budget is surface absorption. This has to do with dark colored objects which do not reflect light energy back but instead absorb it and get hot. Surface absorption occurs when energy reaches the Earth's surface, which heats up. How much it heats up depends on the nature of the surface. For example, if the surface can conduct heat away, the surface will remain cool. But if the energy remains concentrated at the surface warms up. The fourth component of daytime heat energy is from sensible heat transfer. Sensible heat transfer refers to chunks or pockets of air moving into and out of the area being studied. We know, for example, that air that is warmed by the surface will rise and be replaced by cooler air. This is called convection, and the transfer of heat energy in this way is known as convective transfer. Component 5 is long-wave radiation. Long-wave radiation refers to the radiation of energy from the Earth, which is a cold area, into the atmosphere, and for some of this energy eventually into space. But there is also a downward movement of long-wave radiation from particles in the atmosphere. The difference between the two flows, upward and downward, is known as the net radiation balance. The movement of the longest wavelength is likely to win out. The sixth and final component of heat energy in daytime is from latent heat transfer. Another word for this is evaporation. It's known to you, and it occurs when heat turns liquid water into water vapor. In contrast, when water vapor is cooled down and the heat is released, vapor becomes a liquid. As a result, when water is presented on a surface, an amount of the energy available will be used to evaporate it, and less energy will be available to raise local energy levels and temperature. You now know enough from the daytime energy budget. Remember, you should specifically be able to distinguish between latent and sensible heat transfer. Can you do that? We can help you. Listen up. Sensible heat transfer. Sensible heat transfer is when a hot surface heats up the air so that it rises and gets replaced by cooler air, which is convective transfer of heat energy. Latent heat transfer is evaporation when the heat turns liquid water into water vapor, or water vapor is cooled down and vapor becomes a liquid. You should also be able to define albedo. Can you do that? Albedo is reflective heat transfer from a surface. Next, we can look at the nighttime energy budget. At nighttime, obviously, the sun does not shine, so heat energy will not come from the sun. But remember, the term nighttime energy budget is not only about incoming heat, but also loss of heat. The nighttime energy budget refers to the gain, transfer, and loss of energy during the night. The nighttime energy budget has only 4 components, which are long-wave radiation, latent heat transfer, subsurface, and sensible heat transfer. We'll look at these four components in more detail. First, long wave radiation. Can you remember that we said long wave radiation is the upward radiation of energy from the Earth into the atmosphere, some of which is cancelled out by the downward movement of long wave particles radiating from the atmosphere. We said the difference between the two flows, upward and downward, is known as the net radiation balance. The longest wavelength will win. Now, on a cloudless night, there is a large loss of long wave radiation from the Earth. The heat rises into space so that the Earth cools down. But on a cloudy night, the clouds block some of this long wave radiation towards space so that the heat returns to the Earth's surface, thereby reducing the overall loss of energy. The second component of the nighttime energy budget is latent heat transfer, which is evaporation in daytime, but at nighttime it is condensation. Heat energy is released when water condenses. This happens because at night water vapor in the hot air near cold surfaces can cool down and condense from water. This is latent heat transfer in the form of condensation at night. Thirdly, we looked at subsurface supply of nighttime energy. The subsurface of the Earth refers to the layers below the Earth's surface. Subsurface heat supply then refers to the heat baking on soil and bedrock during the day, which rises back to the surface at night to cool it down again. Finally, we look at sensible heat transfer at night time. Do you remember what sensible heat transfer was? Sensible heat transfer referred to air movement. Cold air moving into an area will reduce temperatures, while warm air supplies energy and raises the temperature. We call it the convective transfer of heat energy. Listeners, learners, you are required in the exam to describe how albedo reflection varies and different surface covers. Listen well, it depends on the input and outputs of heat energy to and from a surface. You should be able to list the main differences between two local energy budgets. At night it is cooler than during the day because at night time long wave radiation of energy from the land back to space is not counted by insolation as would happen during the day. At night there's less short wave radiation and more long wave radiation and greater convection. The ground temperature is also hotter during the day and cooler at night because by day the land is heated through the process of conduction. At night, though, heat energy is given up by the ground. Radiative cooling is effective at night. There is no radiative cooling during the day when the sun shines. So, when you get asked in the exam to describe and explain local energy budgets in terms of input and output analysis, with reference to the daytime and nighttime energy model, there are the factors you will refer to. We wrap up today's lesson by reminding you of the key points in the lesson on the local energy budget. The local energy budget refers to the amount of energy that reaches, warms up, and leaves the Earth's surface in one specific location over a 24-hour period, meaning one day and one night. You will be required to know albedo, which is heat energy reflection, and describe how it varies with different surface covers. Remember, to make sure you can distinguish between sensible and latent heat transfer, and check your textbook to study how to draw the daytime and nighttime models. This brings us to the end of our discussion for Lesson 2. NAMCOL has many more radio lessons that can help you brush up on exciting school topics in your grade 12 geography curriculum. I look forward to speaking with you again soon for Lesson 3. Until then, happy learning. Goodbye.
This lesson is produced by NAMCOL with funding from the Ministry of Education, Arts and Culture.